chemistry. Welcome back. It is Monday. I hope you guys had a good weekend. Today we're talking about 13.3 changes of state. Matter can exist in any of three states: gas, liquid, and solid. We've talked about those in the past. Matter cannot be created or destroyed. It can't be changed between different states. Here I have a graph showing all the different changes that are available. We're going to talk about most of these. We're not going to talk about deposition much in this section, but we are going to talk about the rest of these today. Equilibrium. This is a dynamic condition in which two opposing physical or chemical changes, we're going to talk about chemical later, mostly just physical this chapter, occur at equal rates in a given closed system. Closed system means that it has a constant mass. Your book uses the example of a busy department store during the holidays. The number of people going in equals the number of people going out. There's always about the same amount of people in the store outside of it. This arrow right here, we used it before. This is the equilibrium arrow. This is the equation we go in this direction. Equilibrium and changes of state. A system, that's the sample of matter that is being studied. Example, a beaker of water. Phase is any part of the system that has a uniform composition and properties. In a beaker or a bottle of water, at any point in time you have water, which is just liquid water, or you might have some gaseous water up above it. Both those are two different phases. You have the water phase and you have the gas phase. Condensation, this is the process of a gas changing to a liquid. This picture on the right here shows water droplets condensating on the side of that bottle. Concentration, this refers to the number of particles per unit of volume. So how much of something do you have per area? In our beaker, before the initial concentration of water vapor is 0. When you first have a water beaker, you have no water above it. But some water vapor may escape and return as condensation. Escapes, of course, we talked about how the average temperature of something in kinetics is different than what each individual particle has. So if one particle has enough energy to escape, it will be water vapor, and then if it loses energy, it will return and condensate down as water. Eventually, the rate of condensation and the rate of evaporation will be equal if you have a closed system. So say all this air inside of it's getting caught in my fume hood or another container. Once that equal is met, this is now an equilibrium. So your water plus heat energy goes to water vapor, and water vapor goes backwards to water plus heat energy, and it just keeps happening at an equal speed. Le Chatelliers Principle. Henry Louis Le Chatelier, he was a French chemist who was very active in studying equilibrium in the late 1800s. He created Le Chatelier's Principle. When a physical or chemical system at equilibrium is disturbed by an application of stress, which can be a change of concentration, adding something, a change of pressure, changing the space, or a change in temperature, obviously changing the temperature, the system will attain a new equilibrium position that minimizes the stress. So, for example, we're going to use this water. So liquid plus heat energy goes to water vapor. When heat is added, your reaction absorbs more energy. You have more heat, can react with more liquid, and this will temporarily speed up that forward reaction, that liquid plus heat going to water vapor, until a new equilibrium is reached. The equilibrium will produce more water vapor, so the reaction moves to the right, we say. It's because you added heat, now you have more products. You're making more products, so we draw the arrows like this. The reverse, what happens if temperature is decreased? More water vapor will cool, the reaction will move to the left, you'll have more liquid water. What about volume? If now instead of in my fume head we took it and we did it in my room instead, you'd have a lot bigger volume. What happens? Less water will condensate because it won't touch the container as often. That's what slows it down, is touching that water reduces its kinetic energy and forces it to condensate. So if you have less of that, you'll have more water, less water coming back down. So more water will evaporate until you get that equilibrium remet. So this reaction will move to the right. You create more water vapor. Equilibrium vapor pressure of a liquid. The vapor pressure is the pressure exerted by molecules of a vapor which are in equilibrium with its corresponding liquid at a given temperature. So this requires water to have water vapor instead of evaporated alcohol or something else. if a solid can change directly to a gas, it can have an equilibrium solid pressure. So, for example, dry ice can have a equilibrium solid pressure. Liquids can only remain liquid under certain pressure and temperature conditions. If those are exceeded, it will all become vapor. We call this the critical point. We're going to talk about this a little bit later in this section. Boiling. Boiling is the conversion of a liquid to a vapor within the liquid as well as at its surface, when the equilibrium vapor pressure of the liquid is equal to atmospheric pressure. Boiling is a very special thing. It can only happen during very special conditions. When water only vaporizes off the surface, it is called evaporation. It is not boiling. Boiling, liquid has to go to a vapor inside the container too. So when you get a pot boiling on the stove, that rolling boil where bubbles are coming up from inside, that's water vapor bubbles coming from inside of your liquid escaping out. A liquid does not boil if its equilibrium pressure is lower than the atmospheric pressure. As temperature increases, your equilibrium vapor pressure goes up. That's why water doesn't normally boil, but as we increase the temperature, it starts to boil. When the temperature when the equilibrium vapor pressure and the atmospheric pressure are equal, a liquid will boil. We call this the boiling point. Boiling point. This is the temperature at which the equilibrium vapor pressure of the liquid is equal to the atmospheric pressure. In the mountains, where you have a much lower atmospheric pressure, it takes longer to boil water and to cook in those areas than at sea level. This is why it takes a lot longer to boil an egg here than it does down at the Oregon coast. Pressure cookers elevate pressure and increase boiling point so you can get water hotter than normal without it turning into steam. All of it turning into steam. So what they're doing is you're increasing the pressure, you're forcing more of that steam to hit the surface of the water and condensate and then reboil, and it allows you to get the pressure higher. On the graph here, this one says that it goes up to 250 temperature versus your normal 212 degrees Fahrenheit, boiling point. Molar heat of vaporization. This is the amount of heat required to vaporize 1 mole of liquid at its boiling point. The magnitude of this number is a measure of how strong the interaction between particles are, how strong those London dispersion forces are, those dipole-dipoles, those hydrogen bonding, covalent bonds. The stronger the attraction, the more force needed to overcome it, and therefore higher molar heat of vaporization. Each liquid has its own value. On the chart on the right, you can see acetone boils at a much lower temperature than water. So does methanol and benzene. It's likely that we are not made of these substances because we would potentially boil. Freezing. This is the physical change of a liquid to a solid. Its liquid goes to a solid plus heat energy. Freezing point. This is the temperature at which the solid and liquid are at equilibrium at 1 atmospheric pressure. At this point, the liquid and the solid have the same kinetic energy. Melting. It's the opposite of freezing. Melting is the physical change of a solid to a liquid. Melting point is the temperature at which the transition from the solid phase to the liquid phase occur. The melting point and the freezing point should happen at the same temperature. For example, for water, they're both 0 degrees Celsius. At 0 degrees Celsius, water both melts and freezes. The equation for melting would be solid plus heat energy goes to liquid. Sublimation. This is a change of a state from a solid directly to a gas. For ice, which is made of water, sublimes at temperatures lower than 0 degrees Celsius. So this is why in cases where you have a thin layer of snow and it's still below freezing, you can still have it disappear. This water will sublime into gas and then escape into the atmosphere. Frost-free refrigerators use this to rid their compartments of excess liquid. They heat up the ice just a little bit to get it to just that sublimation point, and then they use a fan to blow off that extra water. Phase diagrams. These are graphs of temperatures that are temperature versus pressure that indicate the conditions under which the gas, liquid, and solid phases of a particular substance exist. Triple point, this is an interesting area where it's the temperature and pressure conditions are just perfect, where you get solid, liquid, and vapor of a substance all at the same time. So this water, for example, will be going between gas, liquid, and solid all the time. You'd have sublimation, freezing, melting, evaporation, boiling, all happening at once. The critical point / critical temperature, we call this is the temperature where only the gaseous state can exist. You no longer have solid and liquid. And the critical pressure, this is the lowest pressure required for a substance to exist as a liquid at critical temperature. So in this phase diagram here, you have solid ice, liquid water, and water vapor as a gas. So this line here is kind of showing you where everything's going to split off. So at less than 0 degrees Celsius, at a normal atmospheric pressure of 1 here, you're gonna, this is in pascals, so this is your normal atmospheric pressure right here is 101 pascals. Your freezing point is 0, and your boiling point, where it goes to water vapor, is 100. So this shows you the triple point here is at 6.6 atm and 0.01 Celsius. This is where your water will go from ice to liquid to gas all at the same time. If you get above this in temperature, it will either, if you're depending on your pressure, be a gas or a liquid. So if you're at 101 pascals but 300 Celsius, your water will be a gas. If you're at 101 pressure and you're at lower than 100, in between 100 and 0, you're going to have liquid water. And if you're at the same 1 atmosphere and you're below 0 Celsius, you're going to have ice. So that's kind of how you read this chart. If you take your pressure and your temperature, and then it will show you exactly where you should be on this chart. It'll show you whether you have a solid, gas, or a liquid. Section review for this section is on page 390. It is questions 1 through 6. I just answered number 6. So if you guys want to go back and rewatch that part, you guys will have the answers for that one. Hope you guys had a great weekend. I'll see you tomorrow.